T-minus 20 seconds and counting. 11, 10, 9, 8, 7. We have a go for main engine start. 5, 4,
oh, there it
3,
goes.
2, 1.
Oh.
We have booster ignition and liftoff. Houston now controlling the flight of Columbia, the International Research Mission finally underway.
My space science career started when NASA first started accepting applications from women, and I was selected in 1983. I trained for 9 years and flew on Space Shuttle Columbia on STS-40, the first dedicated medical mission for NASA. My name is Dr. Millie Hughes-Fulford, and I'm a principal investigator on a NASA grant where we study immunology. I'm interested in finding out why the T cell is immunosuppressed in spaceflight. And it's not only important for space travel, it's also important here on Earth for people that have immunosuppression like HIV infection. The first time NASA realized there was a problem was on the Apollo missions, where 15 of the 29 Apollo astronauts had infection either during the flight or immediately after flight. The Apollo astronauts were recovered from the ocean, and the next time they were shown on television they were wearing biohazard suits, and that's because NASA was concerned about them bringing back foreign bacteria from the moon.
Now the 3 men wearing biological isolation garments enter the mobile quarantine facility and their earthly confinement.
In the 1970s, there were follow-up studies on Skylab. And the scientists took blood samples from returning astronauts, and they then activated the T cells in those samples. What they found was that in the returning astronauts, the T cells did not activate. And that was compared to the backup crew that had not gone into space, and they had normal T cell activation. From that data, we found out that something is happening to human beings in spaceflight that keep the T cell from activating properly. Immunosuppression is serious, not only for people in space that have immunosuppression, but here on Earth, like an HIV patient. People that have immunosuppression can live normal lives, but if an event occurs like a serious cut or they breathe a lot of bacteria into the lungs, they can have an opportunistic infection. If that happens, they can end up hospitalized, or the infection can even cause death. In 1983, Dr. Augusto Cogli, European Space Agency investigator, started looking at the isolated T cell. And so he put one group of T cells up in space, the other group of T cells stayed on the ground. What he found out is that when the cells were in spaceflight or in microgravity, they didn't activate. And that was the first time that we realized that gravity or spaceflight had a direct effect on single cells in humans.
We have a go for main engine start. 5, 3, 2, 1. We have booster ignition and liftoff of Space Shuttle Columbia with a multitude of national and international space research experiments.
Now, BioPack has a centrifuge, so things are exposed to microgravity, and then the centrifuge provides artificial gravity, and you can compare the two types of cell cultures.
I would say the most interesting and probably the most challenging thing that we did was an experiment called Lucan. That particular experiment is looking to see how white blood cells are activated to fight off diseases in microgravity versus how they work in 1G, in an attempt to try to better understand how astronauts, or understand why it is that we are more susceptible potentially to diseases.
We need to know what causes T cell inactivation in space. And we need to know that because then we can start looking at the countermeasures, physical countermeasures or pharmaceutical countermeasures. Things like a physical countermeasure would be we have a human centrifuge on the rocket going, and they can go into the centrifuge and have normal doses of gravity throughout the flight. A pharmaceutical countermeasure would be something like finding some new drugs that would help the T cell activate properly. If we go to the moon and we have a moon base, and we assume that half of the astronauts are going to have some form of immunosuppression, and the moon has less gravity, so you have more bacteria in the air, more dust in the air. They're breathing that in, they might have an infection coming from that. And if you take into account that bacteria can grow twice as fast in spaceflight, you have a recipe for opportunistic infection. I'm going to Russia and then on to the Cosmodome in Baikonur, where we're going to be putting T cells on the Soyuz to go up to the International Space Station. Once they're on ISS, then astronaut Thomas Reiter will conduct the experiments for us and then send them back down, where we're going to analyze them back in San Francisco. By doing these studies, we're going to be a lot closer in understanding what causes T cell suppression in spaceflight. And once we understand the cause, we can start working on the countermeasures that are needed to return the astronauts' T cell to normal function.